Today we're going to talk about thermodynamics, and there's a specific way that physics approaches thermodynamics, and so we will be discussing it from that perspective, and there are certain definitions that have to be very clear when we talk about thermodynamics. So the first of those is the term system. A system is any portion of the universe that the individual chooses to study. So you would potentially draw a circle around whatever area you want to take into consideration, and that would be called the system. And it is important to define that whenever you do a problem in thermodynamics, because what occurs between the system and the next part, which is called the surrounding, is very important to be clear about. And the surroundings, or the surrounding, is any aspect of the universe that's not considered part of the system. So you have the system and the surrounding. The first law of thermodynamics says that the delta U, which stands for the change in internal energy of a system, is equal to the heat of that system minus the work of the system. Now, when I specifically wasn't totally clear what I meant by heat and work, it's actually the heat absorbed by the system, and minus the work performed by the system. And you'll see in the next slide that we actually have a way of expressing all the aspects that can occur. So a positive work is positive in sign when it is done by the system on the surroundings. We have to be very clear about this. For the formula we just had in the previous slide to work, we have to use this sign convention. So we have to be very clear that if it's a work done by the system on the surroundings, then it's positive. Conversely, if it's work done on the system by the surroundings, then it's negative. And obviously, since it's subtracted, a negative and negative is positive, so it represents an increase in the internal energy. So another way to think about this is that work done by the system decreases the internal energy of the system. Work done on the system increases the internal energy of the system. Heat, on the other hand, is just the opposite. Heat added to the system by the surroundings is positive. Heat taken from the system by the surroundings is negative. And so again, if you think about it in terms of internal energy, if you add the heat to the system, you increase the internal energy of the system. If you take heat away from the system, then you decrease the internal energy of the system. So here's a diagram to help show what I've just said and help review this. What you can see here is, here's the formula. Here is heat added to the system, so it's positive, and work done by the system, so it is also positive. So the internal energy is decreased by work done by the system and increased by heat added to the system. And you can see the convention is this total heat is going to be the positive heat input minus any heat output. And conversely, the work taken out is the work done by the system minus the work input. So the total would be positive. It's purposeful that this arrow is narrower than this arrow, so the total is a positive number, and that this arrow is bigger than this arrow, so this is positive. Internal energy of the system is the sum of all the kinetic and potential energy of the system's molecules. This is a molecular definition of the internal energy. Remember, this represents the change in internal energy. This is the absolute value of the internal energy. It's the sum of all the kinetic energy and all the potential energy of the system's molecules. So changes in internal energy, and this is another important aspect of this, is path independent. That is to say, it doesn't matter how one gets from the starting point to the ending point. the change is the starting point minus the end point, regardless of how it occurs. So for example, you have two different processes that result in the same delta U. The first is shown in diagram A here, where you have a total of 15 joules of heat transfer taken into the system. That's 40 minus 25, so the total is 15 joules in, or a positive 15. And at the same time, the work performed is a total of 6 joules, which is 10 joules output and 4 joules input. So the total is 6 joules of output. So delta U here is going to be 15 minus 6, or positive 9. So the internal energy increases by a positive 9 joules. System B here, what you have is the removal of 150 joules of heat from the system, but at the same time 159 joules of work are performed on the system. So you do the math here, and it's minus 150 minus a minus 159, and you end up with a positive 9. So both of these are remarkably different in how we get there. However, you end up with the same change in the internal energy. Well, when we talk about how this occurs with people, food is taken in, but it's not taken in directly as heat or work. So it is a form of energy, and it's a positive form of energy, but it's not actually heat put out or performed on the person or put out by the person. And so if you look at the first law of thermodynamics in terms of metabolism, heat is transferred out of the body, so it'll be negative, and work is done by the body, so it is also positive. At the same time, so overall you end up with a removal of internal energy, but the food intake acts to replace it, and the food is what is used to provide the work done by the body and the heat lost by the body. In a plant, the sun actually has an input of heat. At the same time, the plant loses heat, but the amount of heat lost by the plant is less than the amount of heat gained from the sun, so the overall delta is positive. And this, if this person ate this flower, this energy, this stored energy, would then be used by this individual in order to do their work and also put off heat. So let's take a look at a couple problems, and the good news is that I've fixed my pad, so the handwriting hopefully will improve. The first problem is shown right here, and what we have is what is the change in internal energy of a system which does 4.5 times 10 to the positive 5 joules of work, while 3 times 10 to the 6 joules of heat transfer occur into the system, and 8 times 10 to the 6 joules of heat transfer into the surroundings. So you have both a transfer of heat out of the system into the surroundings and into the system at the same time. So how would we go about doing that? Well, we know that the formula says that delta U is equal to Q minus W, and the total amount of heat on the system is 3 times 10 to the 6th, and then that's plus a minus, because then the other heat is transferred out of the system, so it's 8 times 10 to the minus 6 out of the system, so the total heat transfer is a minus 5 times 10 to the 6th. It's not minus 6, it's plus 6, excuse me. At the same time, the work performed is performed by the system, so it's positive, so it's 4.5 times 10 to the positive 5. So if we put this in, we have minus 5 times 10 to the 6th minus 4.5 times 10 to the fifth. So the total change in internal energy is 5.45 times 10 to the 6th joules. So that's the first problem. So the internal energy of this system would lose a total of 5.45 times 10 to the 6th joules. The second problem says, what is the average metabolic rate in watts, which is joules per second, of a man who metabolizes 10,500 kilocalories of food energy per day? So 10,500 kilojoules, of food per day. So this first part, power is equal to heat divided by time, and so we have 10,500 kilojoules divided by 1 day times, and there are 1,000 joules in a kilojoule times, and there are 1 day has 86,400 seconds. And if we do the math here, we end up with 122 joules per second, or 122 watts. So that's the power, the average metabolic rate in terms of watts. B says, what is the maximum amount of work in joules that he can do without breaking down fat, assuming an efficiency of 20%? Well, efficiency is equal to the work divided by the energy input. And so work is going to equal the efficiency times the energy input. And we have the energy input as, so it's 20% efficient times 10,500 times 1,000 again to change it to joules. And if you multiply that out, that's 2.1 times 10 to the 6th joules of work. The last part says, I'm sorry, that is the last part. My bad. And so those are the problems related to what we were just doing. Now let's take a look at some application for the first law. And the first is something called a heat engine. A heat engine is a device that uses heat transfer to do work. So here's an example. Here's our system right here. What happens is you take in heat, the internal energy change you want is 0. So that this does not accumulate increases in internal energy. So based on the first law of thermodynamics that we just discussed, we produce a certain amount of work and we have a certain amount of heat output. And obviously this plus this has to equal the input of heat, or the work done has to equal the input of heat minus the output of heat. So here's an example of how this works. So first of all, we have a piston, and the heat transfer of a gas in a cylinder increases the internal energy of the gas, creating higher pressure and temperature. So heat is coming in, you increase the temperature and the pressure. This heat increases the internal energy, and that's equal to the intake of heat by this situation. Then we move to B, and B, work is performed. The force times the distance here represents the work that's performed. There's no further heat input, so the second change here is going to be equal to the work output. So as the force here moves the piston and the gas expands, then this is the internal work done. This is the work done, and it decreases the internal energy from the absolute value that was up here to here. So it's going to be a negative output of work. Now if you think of it in terms of it's work done by the system on the surroundings, so it's a positive number, but it's it's a loss of internal energy by the system. And then the third is heat transfer to the environment occurs, and this happens when this pushes the heat out after this expands, and the piston can then return to its starting position and then come back up to this point right here. So an isobaric expansion of gas requires heat transfer to keep the pressure constant. Isobaric, iso means the same, baric means pressure. So this is to keep the pressure constant, you have to have an input of heat here. Since the pressure is constant, then work is done in order to push this into a larger point. And when we return to the next part, we will do some problems related to this. Down here, the work is equal to the force times the distance. The work here, the force here, is equal to the pressure that's distributed over this area. The pressure being newtons per square whatever, and the area being the square whatevers. So you end up, this multiplied together gives you newtons of force. And then this right here is the distance. And then area times the distance is the change in volume. So pressure times the change in volume is another way to express the work.